Hi, my name is Julia Fleischman, and this is my Lab 3 report. Today we will be doing a lab on black holes, and we will go over the purpose of this lab, both computational models, and get some further understanding. So the purpose of today's lab is to observe a stars in a spaceship's orbit near a black hole, find the mass of the black hole, determine the initial velocity needed to escape the black hole via spaceship, and we will model this through GlowScript. But before we start, it is necessary that we go over the fundamentals. One of those is the momentum principle, which is derived from Newton's second law that states that the total change in momentum with respect to time is equal to dp dt parallel plus dp dt perpendicular. We also have the velocity update formula, which is v final equals v initial plus f net delta t. With that comes the position update formula, which is also similar and is r final equals r initial plus v average delta t. But since in today's lab we are dealing with non-constant forces, V average will be replaced with V final. Finally, we have the universal gravitational force equation, which can be seen on the screen with G representing the gravitational constant, M1 and M2 representing the mass of two different objects, and R being the radius between these two. We are interested in finding the mass of the black hole, so in order to do so, we must rearrange the equation as seen on the screen. Our system in part 1 of the lab is the star, and in part 2 it's the spaceship. The surroundings include the black hole. The star mass is given us to be 2.0 e30 kilograms, and we then discover that the mass of the black hole is 7.75 e33 kilograms, and the initial velocity needed to escape is negative 4 e7 8.3 e6 meters per second. In our first computational model, we are trying to find the mass of the black hole. In order to do that, we had to calculate fnet, fnet parallel, and fnet perpendicular. Here in the code, we inputted the necessary variables to start the process with the gravitational constant, the given star mass, and delta t, which is just the amount of seconds in one day. I then inputted the formulas formerly discussed to calculate the initial and final velocity and position of the star that was near the black hole. Then, in the second to the last line, I inputted the momentum principle and said that F net was equal to dp dt. We are able to do this because according to Newton's second laws, the momentum and net force are equivalent. In this section of code, you can see many formulas being ran through the program to calculate all three net forces, normal, perpendicular, and parallel. We can then use these equations to solve for the mass of the black hole. When the code is ran, we are given this image and the values for our three net forces and the black hole's mass, which is 7.57 e3 kilograms, are given. Having our black hole's mass, we are now able to move on to the second part of our lab. For our second computational model, our goal was to calculate the net force on the planet and the spaceship to be able to determine the initial velocity needed to approach the black hole but not get sucked in. I inputted the black hole's mass from the first model into our new code and kept the constants we already knew. To be able to accurately predict the velocity, it is necessary that we account for all net forces, which is what is being done here. We calculated the net force of black hole on the planet, ship on the planet, black hole on the ship, and planet on the ship. We then applied Newton's second law and used the velocity and update formulas to determine the velocity needed. When we run this code, we are returned with this image. The cyan line represents the planet's trajectory, and the magenta line represents the spaceship's trajectory. Through trial and error, we determined that the velocity needed to approach the black hole but not be consumed is negative 4 e7 8.3 e6 meters per second. When observing the differences between these two codes, it actually reveals the relationship between the two. As the planet gets closer to the black hole, the mass of the black hole also increases, and vice versa. We also cannot forget to mention possible sources of error. The entire simulation here is very approximated and does not accurately report the mass of the black hole since the code takes the average mass of the black hole. Additionally, when I inputted the mass of the black hole into the second code, I rounded it to 2 decimal places and did not keep the 8 or so that followed after that. This causes rounding errors and once again does not accurately reflect the real-life situation. So after this lab, you may be wondering if there's a difference between net force and its parallel and perpendicular components and the rate of change of momentum and its components. And there actually isn't. Newton's second law states that net force is equal to delta p over delta t, with p representing momentum, and delta p over delta t is the rate of change of momentum. Lastly, if I wanted to establish an orbit around the black hole, what would my initial velocity have to be? Once again, after trial and error, the necessary velocity needs to be negative 2.5 e7 5.34 e6 meters per second. Thank you so much for watching.